Over the course of these live lessons, we've experimented with quite a few different architectures. I have explained that bidirectional LSTMs, particularly stacked ones or in combination with convolutional layers, they'll probably give you the best results in general. But with this data set we've been working with, the IMDb data set, the relatively small size of it has meant that a convolutional structure with just convolutional layers that we tried out quite a bit earlier has been the best performing network we've had yet. So let's revisit that performance. So the best validation accuracy it had was 89.2%. It also had an area under the curve of the ROC curve of 96%. So this is the best model we've seen yet. So given the constraints of this smaller data set, is there something we can do, something clever we can do, to get even higher accuracy out of it? And I have an idea. So let's copy this notebook. If you want to use a pre-completed notebook, you are welcome to check out the multi-convnet architectures notebook here. I'm going to shut down these notebooks, the previous notebook that we had running, to free up all of our resources for our current effort. So let's call this a multi-convnet convolutional sentiment classifier. Change our title quickly. And in this notebook, we build a multi-convolutional neural net to classify IMDb movie reviews by their sentiment. That sounds good. So let's clear our outputs. And we are going to have the same dependencies as we had before. Those don't change. With respect to our hyperparameters, we also will not be changing very much, but we're going to change the directory name to multi. Epochs and batch size, those can stay the same. Our vector space embedding can stay the same. However, we are going to make some changes to our convolutional layer architecture. So now we're going to have multiple convolutional layers, but not stacked adjacent to each other. So I'll explain that more fully in a moment. We're going to have all three of our convolutional layers have the same number of filters. We're going to leave them all at 256. What we are going to change is our kernel size. So the first kernel, we can leave that looking for sequences of 3 words that indicate sentiment, but we're also going to add in 2 new convolutional layers that are looking for sequences of length 2 and of length 4. Our dense layer architecture can stay the same. So let's execute that cell. We load our data in the same way, pre-process our data in the same way, but we are going to completely change our neural network architecture. So we can actually just delete everything that's in there. We're going to be creating a completely new architecture. This far, we have been using the sequential model. So we've been using a Keras model where all of our layers pass in sequence from one to the other. We're going to make a change to that now, where our embedding layer will pass ultimately into 3 different convolutional layers that will then feed into a dense network at the top, and then that will itself go into the output layer. So there is a change that we need to make up here in our dependencies. We need to change this sequential to model. It's the first time we're doing that. And then we're also going to need some additional layers, which are the input layer we haven't had to deal with before, and a concatenate layer to concatenate our 3 convolutional layer pillars together. So let's rerun that dependencies. cell. All right, so previously we always said that we were having a sequential model at the top of this neural network architecture cell, but now we are not going to. So first, let's just replicate a single convolutional layer with this new kind of setup. So now we need to specify quite a bit more. So we're actually going to name our layers. So we're going to have an input layer, and it's going to be of type input. It has a shape that we need to specify. Previously, this was happening automatically, and its shape is the max review length. You need to put that comma in there because it changes the orientation into the orientation that we need. Our data type is going to be an integer. int16 supports integers up to plus or minus 32.7, and we are subsetting our vocabulary to just 10,000 words, so that's more than enough precision. And we are going to assign a name, so this will be helpful later when we look at the summary to assign the name specifically here in the singular. Okay, so that's our input layer. We're also going to have an embedding layer, as we did before, but we need to now specify that explicitly. It's going to be an embedding layer. It's going to have the same parameters as it did before, so the number of unique words and the number of dimensions. The input length is equal to max review length again. And we're going to give it a name, which is embedding. Now we're going to do something that we have not done before, which is that we need to explicitly specify that this input layer is feeding into the embedding layer, and we do that with this second set of parentheses. It's an interesting way of annotating it. And we're going to be doing that in each of the layers with this second set of parentheses. So in our embedding layer, we are also going to have dropout, so we need to name that layer our dropout embedding layer. That will incorporate spatial dropout 1D. It will have the same parameters as it had before. We need to give it a name. And we need to explicitly say that our embedding layer will feed into it. Now we're going to start off with one convolutional layer. It's one-dimensional because NLP data are in a one-dimensional sequence. And it will have the number of filters and filters of the size that we specified above. This first one is filter length 3. And it's going to have ReLU activation as we typically use in our hidden layers. And we need to assign it a name, convolutional layer 1. And we need to tell it that it's getting its input from the drop embedding layer. Okay, now we're also going to have global max pooling. So we need to specify that here, global max pooling, and we need to give it a name, max pooling 1, and like all the other layers, we need to specify what layer is feeding into it as an input. Okay, so we're going to leave space here for our other two columns. So now we're working on one of our 3 columns that will feed into the output layer, but let's just worry about one first and make sure that runs before we deal with the other complexities. So we are going to have a dense layer, and it is going to have the same parameters as it did before, the number of neurons in it. It's going to be ReLU activation like the other ones. And we need to assign it a name. And we're going to have it take in input from this max pooling layer here. Okay. We're going to have dropout in that dense layer, so let's make that explicit. And it's going to drop out the proportion that we specified above, assign it a name, and have it be fed information from this dense layer right below it. And then that will feed into an output layer that gives us our predictions. So that output layer is dense, just like it was in all of our previous notebooks. It's a sigmoid neuron. We need to name it as our output layer now. And it needs to take input from this previous layer. So that's pretty much it. We just need to specify one last thing, which is the actual model. So we used to do that at the beginning of the neural network architecture cell. Now we're doing it at the end. We're saying that the model will run from the input layer to the predictions that it outputs. So let's have a look at that. So our neural network architecture is all defined. You can have a look at the model summary here, and we can see that everything lines up properly. Input layer feeding into embedding, some dropout, our single convolutional layer for now into a max pooling layer, and then our dense layer with dropout into our output layer. So our model configuration stays the same, and our fitting stays the same. So that's all pretty straightforward. Now, instead of waiting for this to train, we know now we can be satisfied that everything is lined up properly. Let's head back and set this up for having not a single convolutional channel, but 3 of them all together. Great, so this finished running. Most of the time was spent loading the memory onto our GPU. It actually took very little time once the GPU was actually loaded and running. So we see that our accuracy is very high, on par with the highest that we've seen throughout these live lessons. And we've attained an area under the curve that is also on par with the highest we've seen. So it's, about the same, 96, like our previous convolutional sentiment classifier. So now let's add in those other 2 convolutional legs. So to do that, we can copy and paste this first leg. We just need to be sure to go through and make changes so that we change all of our 1s to 2s here in the first one, and that we change all of our 1s to 3s in this third one. Now we need to add in one more. It's not really a layer. It doesn't, do any processing. It just combines our 3 legs that we have together again. It puts them side by side for input into the dense layer coming up. So it's called a concat layer. So here we'll specify concatenate, and it takes in max pool 1, it takes in max pool 2, and it takes in max pool 3. Now there's one other change we need to make here. So let's have a quick look through. We have our input layer, that feeds into the embedding layer. The embedding layer feeds into the embedding dropout, and then the dropout embedding layer feeds into the first, the second, and the third convolutional layer. Cool. So that's set up here, 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 and then each of the convolutions passes into its own max pooling layer. So conv1 into max pooling 1, conv2 into max pooling 2, conv3 into max pooling 3. And then the concat layer ties those 3 convolutions side by side for input into the dense layer. So we need to specify that the dense layer is taking in from the concat, and then the remaining layers, the dropout and the output, remain the same. There is one last little thing I want to do just for fun, which is adding in a second dense layer. So we'll copy this top dense layer and we'll make dense layer 2. And dense layer 2 can have the same parameters as the first dense layer. Let's just leave this as n-dense. And drop dense layer 2 will take its input from dense layer 2. Dense layer 2 will take its input from the first drop dense layer. Cool, so now we have a pretty complicated architecture. We've got input layer into embedding layer, through dropout into 1, 2, 3 convolutional layers. Those 3 convolutional layers get concatenated together side by side. They feed into a first dense layer, a second dense layer, and an output layer on top. So we've got a seriously deep neural network here now. Let's make sure in our model summary that everything is looking good. kconv2 is not defined. Yeah, I need to rename these kconv2 and 3. There we go. Let's look at that again. There we go. Just gonna zoom out a little bit so we can see everything in one go. So we've got our input layer into embedding, dropout, then our 3 convolutional legs, all taking input from the drop embedding layer. Those feed into their respective max pooling layers. All 3 max pooling layers feed into the concat layer, which itself feeds into the dense and the drop dense. We're not seeing our second dense layer here, so something is amiss. Drop dense layer 2 into dense layer 2. Oh yeah, we're skipping over. We need to specify drop layer 2 into the output right there. So there we go, that's a quick debug. The name dense is used twice. Yep, we need to name this dense 2 and drop dense 2, no problem. It's pretty easy to debug these. And there we go. Our model is all set up. Let's restart the whole notebook and run all to see what happens. So instead of watching this slowly fit, which I had down as, well, actually only about 6 seconds per epoch, but I have the results here all ready for you guys. So after all that, with our very complex architecture, we end up with a validation accuracy of 89.5%, which is the best that we have had. So our convolutional network's validation accuracy was the previous best, 89.2. So now we're seeing 89.5. And our area under the curve is 96.1. So that is the first time that we're over 96% comfortably. This is the best model we've built. I hope you enjoyed seeing all this stuff stacked together, and then also being able to have multiple different legs merged together. There are a ton of places that you can go from here. We will talk a little bit about hyperparameter tuning options next.